There were a number of findings of the mission, major findings. And first and foremost, I think your observations supported the hot Big Bang theory of the early universe. And can you reiterate again just why it supported this theory?
Yeah, basically, the observation that the spectrum is perfectly in match with the prediction is the clincher. None of the competing theories could come anywhere close. So
Like
what
the
are the
static.
competing theories? So there was an idea that the universe was static. That was Einstein's. Well, that just couldn't be right. It was shown immediately that it wasn't from observations. And also eventually Einstein saw that even his idea was unstable. It could not have been static. So it wasn't static, but there was another one that was popular called the steady state, which is not exactly static, but it said the age of the universe is infinity, and the way that we see it is being, it is expanding, and it's continually being replenished from some mysterious source of material, so that it only looks like it has a finite age. It really has an infinite age. So the trouble with that one was it could not reproduce the spectrum, because in that story, the light does not come from the hot initial conditions where it's cooked to perfection. It comes from later processes of starlight being absorbed by dust grains and then emitting far infrared light or microwave light. So they just never could match that theory to the observations.
So the hot Big Bang theory, just to reiterate and make sure that I have it right, it predicts that there is this early stage of the universe where everything is quite uniform, modulo some densities that result in the anisotropy of the CMB. And you would expect from your instrument to detect this uniform background microwave radiation if the hot Big Bang theory was correct. And that's what you found.
Yeah, exactly right. Yeah.
Okay. What would one have expected for, say, the static universe? What sort of data would have supported that theory?
Well, I think we should skip over that because it isn't static. But if you mean the steady state theory, where it's the expanding but being replenished, then we should have seen a different spectrum, different distribution of heat with wavelength. And if you had seen something that looked like starlight re-radiated by dust grains, then that would have matched that story.
Okay. I see. And then how does inflationary cosmology, so pioneered by Alan Guth, help to account for this really high degree of isotropy?
That basically posits that the early universe was sort of static enough for a while for it to become uniform. Then it started to expand. And so you take a more or less uniform early universe and stretch it out, and it's even more uniform. So that explains several things. One is that we see the temperatures the same in two opposite directions, over there and over there. And you can't see my hand, but I mean, exactly opposite directions. How does the universe get set up so two places that are not in connection now could have been set up to be so uniform when they started? So we say, well, they were close enough together to be the same when the universe was young, and then they got stretched apart by this inflationary story. So we should probably say, what is the proposed idea that behind this? So Alan Guth and his friends invented or suggested that there's certain quantum mechanical ideas that would do this. You imagine a thing called a scalar field that has a certain properties, and then you say it's unstable. And then you say, in that case, it will lead to an expansion that doubles in size about 100 times, at least, and that will stretch everything out a lot. And then when it's done doing that, then it will turn this energy of the unstable expansion into the particles that we see today, the quarks and gluons and protons and neutrons and electrons and all those things that we now have. So it's a hypothesis that's a quantum mechanical process of the early universe with a certain properties that cause the expansion and then produce the particles that we see today.
There are a few other questions that they're not, I guess, directly related to the observations of the COBE, but they're related to the underlying phenomena. And when we train our most powerful telescopes, like maybe the Hubble or the Webb, to the edge of the observable universe, where we reach this sort of murky horizon of billions-year-old plasma, is this the state of the universe that released what has become the CMB?
No, we're not looking, and with that, we're not looking nearly far enough back.
Okay.
With Webb, we can see the first galaxies growing at a 100 or 200 maybe million years after the expansion. And then before that, there was something we called the cosmic dark ages, where there are no particular objects defined, only the cosmic microwave radiation and some gaseous material out there that's not luminous, because no stars have been formed yet. And then before that is what we call the cosmic decoupling. When the universe is about 400,000 years old, the temperature is about 3,000 degrees Kelvin everywhere, and it's high enough that electrons and protons do not stick together. So the early universe is made of plasma, and the plasma is opaque for electromagnetic radiation, because if the electromagnetic radiation bounces off the electrons very quickly. So that's as far as we can see back with getting an image. So when we see the cosmic microwave background radiation with its bumps on the map, anisotropy, that's the universe as it was when it was 400,000 years old, about. In principle, there's more information, but you cannot see it that way.
Right. Maybe gravitational waves, something else.
Yes, indeed. That is the next big thing to go after. If the early universe had gravitational waves propagating in it, then they should have had an effect on the polarization of the spots that we see today. And so that's the big hunt, where my colleagues are busy working on that, and there are thousands of scientists trying to get that answer. Let me tell you a story about why this matters. What's the material like in the earliest universe? Well, here, as an example, with air, we have sound waves, and the sound waves are just compression waves, pressure waves. And but if I had a solid material, then I can also say I've got a stick. I can knock the stick sideways, and laterally propagating the sound waves will go through the wood also. So that means sound waves have three directions of polarization in wood, in solids. In gases, there's only one direction of polarization, which is in the direction of motion of the wave. So now we want to know, well, what's the properties of the early universe? Does it support gravitational waves? What's its elasticity like? So this is a way of getting at it. So that's why it's important.
Yes.
Getting at the nature of the material back then.
Mm-hmm. Well, okay, we've discussed one of the main conclusions. That's the isotropy. So the data from COBE confirmed that the universe is quite uniform. But now for the anisotropy, it's not perfectly uniform. What is the actual variability, the measurement?
Okay. Well, we observed about a part in 100,000 with the COBE satellite. If you get a little bit better angular resolution, which we got with subsequent equipment like the WMAP mission and the Planck mission, it's about 10 times more, because on a scale of about 1 degree angular size, the spots are brighter. And so this is because of the details of how the universe became transparent at its time when it was 400,000 years old. So there were sound waves propagating at that time and making some spots brighter and some spots fainter. So the details are controlling that, and that's why we see that difference. So the way that scientists represent this is what we call a spectrum of anisotropy. How bright are the fluctuations as a function of spatial size? And so when you get at that, you make a plot, and the plot has, you would have think, well, it's about the same at all scales. But then it turns out it's not, because of the details of the events at decoupling. So there's a big peak at an angular scale of about 1 degree, and then there is several smaller peaks at smaller angular scales. So there are about 6 or 7 little peaks that you can find if you really work at it. And if you really believe your story, then you should be able to fit, all the data should fit those 7 little peaks exactly. Which is true, they do, which is a totally astonishing accomplishment.
So the variability itself is variable.
Yes. Variable variability.
Yeah, second order variability, metavariability.
Yep. And there are so many spots on the map that you can get this very accurately.
And how do, you maybe just answered this slightly, but how do theorists account for this variability? Since, I mean, the early configurations of the universe presumably had very low entropy, what resulted in the earliest inhomogeneities that show up in our observations of the CMB? Was it these sound waves that you were referring to?
Yeah. So the picture is, in this, if we start with this, imagine that the inflation that we talked about, this stretches things out over and over and over and over. It leads to a natural prediction that the original fluctuations in the early universe should be about the same brightness on every physical scale, small, medium, and large. And then we say, but we think we understand what happens when the universe goes transparent. And large-scale sound waves won't be much attenuated. The small-scale ones will be, because of astrophysical processes, how the gaseous stuff is moving around. So we start off with something that's smooth and has no bumps on it. And we say, okay, now we think we understand these equations. There should now be 7 bumps. And so then when you get a match, you say, no, I think I really understand. What's left open is what made those bumps in the first place during the time of inflation. And that is unknowable at the moment. But there's one prediction that the inflation story makes, which is really quite remarkable. It says there's something called a spectrum, power law spectrum, which says how much of the fluctuations of small, medium, and large scales, and the number would have been about 1 if you were completely naive, and if you believe this inflation story, it should have been 0.97. And we measured, and it's 0.97, which is a shock to me. I thought we'd never get that to be ever true. When Alan Guth told us this story, I thought you were just making that up for fun. And there would never be any provable anything about it. And now we have not exactly a proof, but it's pretty darn good.
There is another sort of conceptual question that I have here about the early universe being in a low entropy state, which I understand just based on the second law of thermodynamics, that it's going to be lower than it is now. But most examples of high entropy states, they correspond to instances of great macroscopic homogeneity, because it's these states that admit of the greatest number of potential microstates that could result in the same macroscopic configuration. So that's why an omelet, which looks much more homogeneous than an egg, is, you would just assume that it has higher entropy than the egg itself. Now, what is it about the apparent homogeneity of this early plasma, notwithstanding the density fluctuations that resulted in the CMB's anisotropy, that made it such a low entropy state? Is part of it the fact that space is so much smaller and it's compressed? I understand that would have an effect on the entropy or the heat, or what is going on?
Yeah, so honestly, you don't really understand it.
Okay.
So I would better to ask Alan Guth and other people who do.
Sure.
But at least there seems to be no escape from the second law of thermodynamics. We go from lower entropy to higher entropy almost all the time, and quite quickly, because we're talking about very large collections of objects. So basically, you can't beat Mother Nature. So any theory you come up with that doesn't do that can't be right. So
right. I seem to recall something I read. It might have to do with, because of the high temperatures, the Higgs field behaved differently, and things just weren't running into each other. They didn't have masses. But I don't know. I guess that is maybe something.
I don't understand that. Better ask somebody else.
Sure. I'll ask Alan Guth or somebody else about it. But what sorts... So after the data is collected, or maybe while it's being collected, what sorts of precautions were taken, or what sorts of methods were used in the interpretation of the data to ensure that what you were measuring was indeed the CMB, given that all other, as you mentioned, all other sorts of bodies throughout the universe have emitted and continue to emit radiation in the same spectrum, like the Earth is extraordinarily close. And you already mentioned the shield there for that, but everywhere you look, microwave radiation.
Absolutely. The way we sort of go at it is we use our imagination to say, well, what could go wrong? Yeah, we argue and think and toss ideas around for a long time. We make our lists, and then we say, well, if that were happening, how would you know? And what effect would that have on the data? And then you look at the data, does it show up? So as an example, one thing that does show up, we knew that our microwave receivers on the DMR instrument were susceptible to the Earth's magnetic field. And we knew about that when we designed it. We could not completely prevent it. So now what is it going to do to us? So, well, you use your computer and you say, well, if it does that, then this is how it would look on the sky. So you have gigantic computer simulations with adjustable parameters about how do these little magnetic shields work and all these things that you might want to know. And then you say, does this match the reality? And if you adjust the parameters that describe the magnetic shield as well as you can you make a model that fits perfectly? And then you say, yeah, that's pretty good. Let's subtract the model from the observations and see what's left. So that's the number one thing we had to tackle, was the Earth's magnetic field. Then some of the others are a little more subtle, like does the Earth shine over the edge of the sunshade sometimes? Yes, it does. And so maybe the data that are taken on those days are not as good. So can you tell? So basically, every time you think you've got a problem, you may say, if that was true, what would it look like? Can I measure? Yeah, and so we spent a long, long time working on that question, about 6 months between the first pictures that we had that were made by Ned Wright at UCLA. He did his own simplified but accurate computer calculation of the map. He came to our science meeting. He showed us the pictures with the red and blue green spots. Oh, this is real, he says. And then we say, how would we know? So then we started our official process to do what I just described, to think about all the things that could go wrong and test them. And of course, one thing that can go wrong is a person can make a mistake. So you have to do everything twice, at least.
Well, now we've spoken about two of the three conclusions that I wanted to get to that came from COBE. And the third, you already mentioned this early in our conversation, but it was based on the interpretation of the data. The objects that developed after the Big Bang are twice as bright as was once believed. And I think you already said what sorts of objects these were, but how is it determined that they're twice as bright as they once were? And you said that we still don't understand it necessarily, but just what does it have? Just what does it say about our understanding of the universe?
Yeah, well, I think maybe by now somebody perhaps does understand it, but I haven't seen the papers about it. But the sort of presumption was that our extrapolation of the brightness of objects from what we could see with Hubble and telescopes that can see visible light to what do they do at infrared wavelengths was just not right. So if the universe is twice as bright as we thought, then it means half the starlight has been absorbed by dust grains and re-radiated at infrared wavelengths so that we didn't see them before. So that means early galaxies, current galaxies, are dustier than people thought. So lots of interesting surprises about that. Now, getting into the details, that's where it gets exciting for astronomers. And maybe we finally have an answer now, because the Hubble and the Webb together should have been able to see those classes of objects that are now supposed to add up to the right answer for the instrument on the COBE satellite. But I'm not sure. I should be checking my mail to see, has anybody finally answered this question?
Well, that about wraps up the COBE, with the exception of what is the fate of the COBE? Is it still up there? What's its future going to be?
Yeah, its future is it's probably dead, not working anymore. It's lost a few pieces that we know of because they watch it with radar. So it has plastic insulation on the outside, and some of them have flown off.
Because of these space rocks, or just sheer?
Scotch tape gets old.
Okay.
I don't know if it's Scotch tape, but tape gets old.
Mm-hmm.
So it's up there. It's probably tumbling randomly because the electronics probably not working anymore. And its orbit is expecting to keep it up there about 1,000 years. So coming back down to Earth sometime, but not while we're here.
Well, you mentioned earlier this other mission that investigated the CMB, and the one I have in mind is WMAP, so the Wilkinson Microwave Anisotropy Probe. And were you involved in this mission at all?
A little. I was working with the team that proposed it while in the early phases, between the end of the COBE mission and the start of the Webb Telescope mission for me. That was what I was working on. But when I got a phone call from NASA headquarters, would you like to work on this new telescope? I dropped everything else. And I said, I know where this is going. This is the best thing I could possibly work on. So
you're talking about James Webb.
Yeah, I am. Yeah.
Well, now beyond COBE, there's other data. There's the WMAP. How has all of this collectively impacted our understanding of the age of the universe?
We now have an interesting challenge because we have multiple ways of estimating the expansion rate. We have the traditional method of looking at the galaxies receding from us and trying to say how far away are they, and get the distance versus the rate, and that gets what we call the Hubble constant. And we have the other way, which has interpretation of the spots on the microwave map. And we are both quite sure, both methods are quite certain that they're right. Interesting fact is we don't agree between these two methods. So when this first started up, I thought, well, we're just making a mistake with a measurement. But people have been pursuing this question now for a long time, and the measurements are getting better, and the mistake has not been found. So that says maybe nature's telling us something interesting. So the big uncertainty is something we call cosmic dark energy.
Yeah, right,
and of course, we know about the acceleration of the universe. And we gave a Nobel Prize a few years back to the lads who discovered that. And it was a big surprise.
Rees?
Martin.
Adam Rees.
Adam Rees and two other guys. Anyway, Adam was the guy who first saw this effect. He was a postdoc at the time. Really young fella, but he discovered that things did not add up. So anyway, so that we know the universe is accelerating, and it's pretty well described by a single number, which we call the cosmological constant. But now there's no particular reason to think the universe is simple. So maybe there's another kind of thing going on. Maybe the cosmological constant is not a constant. So that's the big question open for scientists now, and we have Lots of new experiments that are going after it. European Space Agency just launched the Euclid mission, specifically designed to go after the evidence from galaxies about the expansion rate and the dark matter and the dark energy. NASA is working on the Nancy Grace Roman Space Telescope, and it's specifically designed to do that. It's even more powerful. And plus, we've got all the calculations from the microwave background and all of the other things about galaxies and all of the wonderful surprises we're getting about the early galaxies with the Webb. So I don't know what's going to happen. Always my initial faith is we made a mistake. But we can't just always say that. Well, we might just discover something interesting.
Yeah, well, the history of science is the history of mistakes, but mistakes that move forward. I think is a good way of explaining it. Well, the last sort of dimension of these cosmic microwave background experiments that I wanted to talk about before maybe we finish with some of your more recent work is what all of this tells us about the geometry of the universe, the shape of space.
Okay. Now, current evidence that I know of is that the universe is expanding and accelerating, and that it's considered to be geometrically flat, which is a bit of a surprise. Space-time in 4 dimensions is not flat, and that is because gravity operates by curving space-time. But if you were to take a snapshot of the universe, say the whole thing as it is now 13.7 billion years after the expansion began, you get a 3-dimensional map. And that's a map in which triangles add up to 180 degrees. It's spatially flat. And why would that be? One explanation is there's some law of nature that we don't know about that makes it so. One would be that this cosmic expansion has stretched out the curvature so it's unmeasurably small. So that's something in favor of the inflationary theory. We start something that is curved and it's not very curved anymore and we can't see it. Mm-hmm. So, yeah.
And then it also could have been saddle-shaped or who knows? There are a lot of options. I'm sure if you speak to string theorists, there are many more dimensions to be taking into account.
And if you go back into the earliest moments you could imagine, then it probably wasn't flat, spatially flat, but it is now.